Good day. Welcome to this session on air conditioning. Today's topic is heat loads. Heat loads is a basic requirement to be able to size, check on the type of air conditioning you require and what is the optimum use that you can put it to. Heat loads would mean the use of a vocabulary which will perhaps take you back to the physics classes which you first had before your undergraduate level. Today you are doing the postgraduate program, so don't hesitate to take 2 leaps back and go back all the way to the physics classes you had first. The chapter of interest would always be heat. Basically, air conditioning is heat. To an average Indian, where we live in a hot climate, air conditioning always means cooling, but it is never so. It can also mean heating in the temperate areas, and anyway, cooling is removal of heat. So let's look back for a few terms of heat load vocabulary that are required. In the slide that you have in front of you, I have just put in a few important items which will come up. Something like the quantity of heat. The quantity of heat is always specified in terms of BTUs in the FPS unit or kilocalories in terms of the SI units. The quality of heat, which would be the temperature, is specified in Fahrenheit in terms of the FPS units and centigrade in terms of SI units. There is a small point in favor of my introducing you to FPS units is basically because air conditioning is strongly founded in America, and America still uses the FPS system for the air conditioning work. The most basic unit that you will be keeping on referring to in terms of air conditioning will always be the ton. The ton is not TON, the ton is TR as mentioned in the slide. Ton of refrigeration. We will see a little later what this ton of refrigeration means. Again, stepping back to that same physics class, I am quite sure you will recall the difficulty with which you had mastered the laws of thermodynamics. Very simply stated, the first law is heat is energy. It cannot be destroyed. The second law is heat is an energy, but it can be moved from a higher potential to a lower potential. Very obvious, very simple, requires no explanation. I won't get into too much technicalities, but these two requirements are so basic that unless one has this in mind, there will be no air conditioning. With the second law of thermodynamics, the first law of thermodynamics says that heat cannot be destroyed, which means I cannot have a room which is, if I have to remove heat from it, since I cannot destroy it, I cannot have air conditioning. But then I take refuge behind the second law. The second law says I can move it. So if I can't destroy it, let's move it out. So in an air conditioning room, what is done is heat is moved out of the room. It is taken out and thrown elsewhere. The path it takes can be due to radiation, it can be due to conduction, it can be due to convection. These three, again, if you will recall, are very simple. Take a look at, I am talking from Chennai, south. The most common thing that we see is coffee. It is served, as you see in this slide, in what is called a dabra. It's a tumbler and a flatter vessel in which it is kept. These are the temperatures that you see on the slide. Basically, the coffee would be at 80 degrees centigrade. The surface temperature of the glass would be 75. The dabra around it, which does not have the coffee, would be at 60. And the red lines that you see on the slide indicate the path of heat flow. The kitchen served you coffee at 80 degrees centigrade, but your lips will not require anything better than 50 degrees centigrade. So until that, you leave your glass standing, the glass will lose heat in the forms that you see there. If it loses heat to air, it is obviously losing, without any molecular movement of the air, it is convection. Down at the bottom, you will find that the glass is in contact with the dabra. The dabra is in contact with the marble, and there you have physical contact which is taking away heat by conduction. So the downward arrow indicates heat lost by conduction, convection, and there is a very small portion being lost by radiation, because the surface of 80 degrees tumbler is also exposed to 24 degrees of marble. So here you have radiation, you have convection, and you have conduction occurring all simultaneously. They can never be made. In most cases, one is predominant, two is predominant. I mean, but you never can have all the three equally done. But all the three will take place. Now, this cooling the coffee that you saw was very simple. It was very cheap. There was no refrigeration involved. Why? Because we were handling temperatures above the ambient. 80 degrees is far above the ambient. There is a cooling media all around. The ambient is my cooling media. So 80 degrees gets cooled down to 40 degrees without any problem. I mean 55 degrees, which I wanted for my lips, in absolutely without any difficulty. Now the same thing, if instead of heating, I wanted a glass of lime juice, can I keep it at 40 degrees centigrade and expect it to become 30 degrees? It will not happen. Or 20 degrees, it will not happen. Why? Because I am surrounded by 40 degrees and my lime juice cannot become lower than 40 degrees. So how does it become lower? By introducing something inside, 0 degrees. Now that is the air conditioner in an air conditioned space. In a glass, you have the ball of ice, which is your coolant. In the room, it is the air conditioner, which is your coolant. Now I had mentioned that we will look at ton, because I will be using this word very often. I will give you an introduction to what is a ton. A ton of refrigeration is the equivalent of the heat liberated by ice, 1 ton of ice, when it melts in 1 full day, in 24 hours. So in other words, you engage a tempo, bring a ton of ice, keep it in a room, and if it melts in 24 hours, that is the equivalent of your 1 ton window air conditioner. I mean, most houses today have window air conditioners or small split units, and the capacities are around 1 ton, 1.5 ton. Should such a machine fail, and you are obliged to, let us say, have cooling, then you will just have to lift the phone. If you have a 1 ton machine, order out 1 ton of ice and keep it in the room. Find a way of spreading that ice is coolant to all over the room, but just imagine the kind of work that is called for. That's the kind of duty your air conditioner does. Let's get down to a little more specific requirements like air conditioning. It's no longer coffee, it's no longer lime juice. A body, as most of us know today, is 38.6 degrees as what the doctor would like us to see, healthy people. Maybe the skin is about 4 degrees cooler. Our skin temperatures are around 34, 35. If they are covered by cloth, maybe the surface temperature of cloth will be a little higher. But bare skin, face, hands today are all around 34 to 35 depending on the person and his metabolism, as also his body temperature. His body temperature generally is always kept constant unless he is not in good health. So with 38.6, there's a 4 degree lag from the surface temperature. Now at this parameter, research has established that a person is most comfortable if his environment is at 24 degrees, which means air conditioning temperatures have got to be 24. Now 24 is also related to a couple of other parameters which are very strong on the air conditioning man's board. These are relative humidity and air movement. At 24 degrees, one wants 55% RH. At these conditions, what you don't see in the slide, you require a small air movement across your body, something like 25 feet per minute. Now, to give you an idea of what 25 feet per minute is, if I had a paper on my table, it should not flutter. A paper fluttering means that the velocity is beyond 25 feet per minute and I am likely to feel uncomfortable. So a person is comfortable with 24 degrees centigrade, 55% RH and 25 feet per minute air movement. Again, going back to where I am talking from, Chennai, my ambient is 40 degrees. invariably the wet bulb at that point of time maximum would be around 28. Now, in such a scenario, when you have hot outside and when you have a cool room inside, heat flows in. Now, that is the job of an assessment for heat loads. You have to evaluate how much of heat is coming in, size the cooling load or the heat load as we call it, and buy equipment to match that. For instance, if you have a heat load of a room at 100 tons, you will need a 100-ton air conditioner. You have a bedroom which requires 1 ton of air conditioning, you require a 1-ton air conditioner. Now, how does heat come into this space? Definitely from, as we saw from the law of thermodynamics, it has to come from outside to inside. The moment it comes from outside to inside, that is one established source. The next is heat from inside. These are the two generic forms that one can ever think of. This slide will sort of split up into saying external and internal factors all literally shown on the same slide. You will see that the external sources are heat from the walls, heat from the roof, heat through glass. This is different from what would come through the walls. The wall heat is generally always assumed to be conductive heat, coming because the outside is hot. One surface of the wall is hot, one surface is cold. Heat moves in through the wall by way of conduction. Apart from it, if there is direct sunlight coming through a window, this is radiation. The sun's heat, so many miles away, so many million degrees centigrade, is transmitted into the air conditioned space without heating the path of the heat. Like that, the radiation is one of the external factors of heat. So, among the external factors, you have heat coming in from the fabric, floor, roof, walls by conduction, radiation through glass, and the fresh air that is always taken in to allow for dilution of the pollution that may occur inside a room. Now, these are the external factors. The internal factors are basically any equipment that you keep inside. Second, you yourself, a person, by virtue of being at 38 degrees centigrade and sitting in a room of 24 degrees centigrade, always heats up the room. He perspires, so he adds latent heat. So, a person adds heat, and apart from it, one of the most basic things is lights. The moment you have light, the light ultimately gets transformed into heat, which the air conditioning man is obliged to collect and take out of the room. As I said earlier, the heat through walls, through roof and floor can be called heat through the fabric of the enclosure. This heat flow always follows a very simple formula, K into A into TD, where K is a constant depending on the type of wall, floor or roof, A is the area of the item being considered, and TD is the temperature across the two. Invariably, when sizing heat loads, these are not taken directly as ambient, they are taken from textbooks where small corrections have been made for various aspects. But basically, it is necessary to know that the heat flow through fabric is by conduction and it respects KATD. K is a factor which you can decide as an architect. A is an area which is imposed upon you by geometry. TD is again something that you cannot do. If you are working in Madras, short of taking the place out of Madras and siting your building in Ooty, that amount of TD will always be there. Now, this is a generic value of that KATD. It shows a brick wall, as a brick wall should be hatched. It shows cement plaster. Now, these are things which one would see. The heat conduction through these elements have different values. Heat flows faster through cement plaster, slower through brick, and apart from it, the thermodynamics man says an outer film and an inner film are always there in any conduction, whether it is the glass of coffee, whether it is the glass of lime juice, or whether it's a brick wall. you have an outer film and an inner film. These outer films and inner films depend upon a lot of factors like velocity of air across them. For instance, now in that cup of coffee, there was an inner film. It was retarding the flow of heat from the cup of coffee to the ambient. If I want to cool my coffee faster, what do? I take a spoon, stir the coffee. What have I done at that point? I have increased the velocity of coffee against the walls of the coffee cup, and that inner film value has decreased. What will happen because of that? Obviously, the heat flow is faster and the coffee cools faster. So, this is what you do when you want a coffee to be cooled faster, you take a spoon and turn it. Now, here, perhaps if you put on a fan, you will find that, the inner film gets vitiated or gets reduced. So, these are factors which, are built in by the thermodynamics man when he evolves the heat through a fabric. Inner film is accounted for, outer film is accounted for. You have these elements built in, and to give you an average idea, a 9-inch brick wall, which is generally adequate for separating an air conditioned space from a 40-degree ambient, you need a 9-inch brick wall which has a U value of 0.36 BTUs per square foot per degree Fahrenheit. This is what you see in red at the bottom of the slide. Now, look at the basic materials that one uses today. You have on your slide a listing of a few common material: marble, concrete, cement, brick. What is necessary is not to remember the values that you see against them, but to have a feel for their being good conductors or bad conductors. For instance, if you make, it is very well known that if you make a air conditioned room out of a tin sheet, you require a larger capacity, more heat will flow to tin. Substitute the tin with a 9-inch brick, fine, you have lesser heat coming in. Substitute it with 18 inches, you have still lesser heat. What is required is a feel of the material you use and the thicknesses that are required to be able to optimize on the type of construction that you should go in for. You look at, for instance, marble, you look at concrete. Between the two, marble conducts more heat. Why? Generally, you can make up your mind and see, oh, it is compact. Because it's compact, conduction will be much better. Molecule to molecule contact is more intimate. Heat flow will be much faster. So, you find a tremendous amount of heat flowing through marble. For the same thickness, concrete will conduct less. For the same thickness, cement plaster will be less, brick will be less, and of course, the lowest will be things like polyurethane foam, where the value is but just about 0.18, maybe about 100 times lower than that of marble. Now, that is as far as the fabric heat gain is concerned. The second item that we had looked at was solar heat gain. Solar heat gain is incumbent only as long as sun comes into the AC space. Obviously, if you want to restrict this, a very simple thing is shade the window, which means sun doesn't come in. Now, I am quite sure, if you look at any fundamental book on air conditioning, a good author will start on by saying shade is the cheapest form of air conditioning. What he meant was that when you shade a space, you take care of things like radiation, etc. automatically. The next source of heat is from fresh air. This again is something that is imposed upon you for a requirement of personal usage. You require a personal indoor air quality, and you need to maintain a certain amount of oxygen level. A certain amount of fresh air is required. The fresh air that you bring in from outside obviously is from the ambient. It is at 40 degrees. It has a wet bulb associated with it of 28 degrees centigrade. Now, that hot humid air, when it comes inside as a requirement for health, obviously becomes a heat load to the air conditioning man. Now, these three factors put together are all that is required from the external sources. Let's go back to the internal sources. Let's start with the most simplest one, light. Everybody knows that lights do contribute to heat. Here, calculation for a heat load from the light is extremely simple. All that is required is to find out the wattage. The moment you have the wattage, multiplied by a constant of 3.41. 3.41 into the watts will straight away give you the heat load in BTUs per hour. The heat load from people. Here again, one would say it's extremely simple. Number of people multiplied by a constant. But here, the constant is not a constant always. The constant depends on, as you see on the slide, things like metabolism, his body weight, the sex of a person, age, space, and the temperature. For example, when an office man is sitting, or like I am sitting and talking to you, if I were not talking, my heat output to the room would be just 450 BTUs. When I talk, maybe I exert myself, maybe I do some movements with my hand, 450 will climb up to 500 BTUs. You who are sitting there will perhaps contribute only to 350. If you start laughing, 350 might become 375. If you start moving about, it might become 400. So that's the kind of variation that's allowed. At the extreme end, let us say if all of us were to have workbenches and we start doing some light bench work, we might, our heat liberated into the AC space might go up to 1400 BTUs. So a light bench work requires something like 1400 BTUs, which is 3.5 times what a person will liberate. Or if I were just watching a movie without too much of movement, my heat load will be barely 300 to 310. To give you an idea between that 1400 and 300, there is a table which has been evolved by ASHRAE, where the metabolism of a person is related to the total heat. So sleeping is related as 0.7. So obviously it's below the daytime limit of 400, 450. When you sleep, you naturally have very little activity. You naturally liberate the minimum amount of heat. When you read, when you sit, that's a time when you have unity as the MET of a person. This unit is called the MET. Metabolic unit is called the MET. Now, one look at it will tell you, you can go up to 3.5 to 4 in an air-conditioned area, which is what we said, from 400 to 1400. Now, comfort is also influenced by the type of clothing one wears. In summer, you find people deriving comfort in non-air-conditioned areas by knowingly or unknowingly shedding clothes. What are they doing? By shedding clothes, I don't mean somebody putting on a bikini. I mean straight away somebody, instead of putting on a pant and shirt, you find him putting on a lungi and a banian. Now, there the clothing level has reduced, which means the insulation between the outside heat and the inside heat, meaning my body, has reduced, and I can be comfortable at slightly higher temperatures. Now, here again, when we talk of 24 degrees as being comfort, what is allowed for is a clothing level of 1, which means a light business suit. I am today in front of you underclothed. If I put on a jacket, I can still be comfortable at 24. But if I put on a winter jacket, which is thick, then my ambient temperature will have to drop from 24 to something lower. Only then I will be comfortable, because this fabric which I am wearing has insulated my body from the ambient. And to make me feel comfortable, the temperature has to drip lower for my equivalent comfort to be maintained. This accounts for two of the major sources of heat. The last source that one normally comes across is any equipment that you may keep. It could be a computer, it could be a motor, it could be any electrical device. Most of us will perhaps encounter only computers and electric equipment. There, it's extremely simple. If you know the horsepower of the equipment, multiply that by 2545. If you know the kilowatt of the equipment, which is again related, multiply by 3410. I am quite sure all of us know that 0.746 kilowatts is equal to 1 HP, which is what you see in the relation between 3410 and 2545 on your slide. It is exactly the same relation of 0.746 is to unity. Again, this is just a constant. You just whatever, let us say, I keep a computer in front of me and it has a flat screen, my wattage perhaps will be 145. But supposing I have a few hundred computers and it's a flat screen, I use the older type of version where the wattage is as high as 250. Then per equipment that I use, I am up by 110 watts. So let us say I have 100 machines, I am up by about 10 kilowatts. So that is where This kind of knowledge of this kind of heat is very useful to determine that you should have heat saving equipment inside which does not contribute to heat loads. What did we talk about? This is the summary. We started off by saying a heat load is a factor of two important things which are shown in Roman numerals: external and internal. External is made up of three elements: fabric, solar and ventilation. Integral is likewise made up of three elements: people, lights and equipment. Generally, all the above are calculated and expressed as TR as we saw at the outset. Now, let us look at simple thumb rules when you are planning air conditioning. In a hot humid climate like Chennai, where you take datum outside as 40 degrees and inside to be 24 degrees. To maintain an office with these temperatures 40, 25, you would look at a figure of 150 square feet per ton. These are with standard internal loads, with standard occupancies, with standard comfort required. Then if the same thing were to be done for an auditorium with the same temperature parameters, you would look at perhaps 10 people per ton. In other words, if you were designing for a 1000 seating auditorium, you would say, look, offhand I know it will require a 100-ton plant. Likewise, if it's a hotel room, which a 3-star hotel might be specified to be 180 TR. If you take 150 square feet per ton, you know that you need something like 1.2 tons per hotel room. Same thing can be extended to other applications like a dining hall, like hospitals, and any textbook can be referred to give you the values. Obviously, if the place were not in Chennai, if it were in Bangalore, what's the difference? Instead of 40 ambient, I will be working on a 35 ambient. So the square foot per ton will perhaps increase. An office will need maybe say 160 square feet per ton instead of 150. If it were in Delhi, perhaps it will become a little warmer. Instead of 150, it might be 145. I don't know whether you got the point when I said if you move at 5 degrees centigrade colder, I dropped the tonnage by 0.2. But when I increased it to Delhi, I increased it only by about a very small fraction. That is because at Delhi, the air is drier and the fresh air load comes down. So the percentage increase may not be directly due to the difference between 40 and 24. There will be a small saving because the fresh air load will be much lower in Delhi as it is a drier climate. In places like Chennai, where we have high humidity, that same air contributes a lot of heat. For instance, if I have 1 pound of air, in Chennai it will be maybe 17.2 pounds BTUs per pound, difference, whereas in Delhi it might be barely about 11. So that's the kind of difference we are looking at. Now, if you know the capacities, obviously the next thing will be not too important, but these are the kind of figures that you would look at in terms of budgeting, in terms of sort of mentally evaluating that should I have air conditioning or should I not have, whether it is cheaper to put in a 9-inch brick wall and save on tonnage, or whether it is easier to put in insulation on the roof. Awareness of this figure helps you to sort of trade off between insulation that you should put on the fabric to improve upon the K value that you would get. Again, when you decide on your air conditioning systems, you will basically require for air conditioning areas AHU rooms. I have in this slide tried to list out the type of rooms that one would need for various types of air handling unit. The moment you know that an office requires 50 tons, the next thing will be where do I provide for 50 tons. So if you go to 50 tons, you see the second element, it shows you that you need a room of 4.5 meters by 4 meters. So you build that in. Now where to build it in, again we will see in some other session. But today you have an awareness of a basic requirement of the size of equipment and where to fit it in physically. This again is data which you may require a little subsequently, but at the moment it is something which is nice to know because it helps you to plan. This slide also gives you an idea of the type of loading that is required for various commercial air conditioning equipment. I think with that I have concluded what I wanted to say. I hope you find it interesting. Thank you.